Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi and today we are going to talk on module Structural Theory of Glass Formation, and this module is under the paper Ceramics. So students, after the completion of this module, you all should be able to understand the structural theories of glass formation, which includes Goldsmith's radius ratio criteria, the Sharration criteria for glass formation, and various other criteria like Smekle, Stanford, Ditzel, and Sun. So here comes phase transformations in glass. A glass can undergo several types of phase transformations. It can crystallize into a crystalline phase or it can undergo liquid phase separation. These two types of phase transformation can occur in more than one way. These are shown already in the figure. The crystallization may occur from the liquid phase, or if the liquid is cooled to a glass phase, then crystallization may be induced by subsequent heating of the solid glass below the liquid formation temperature. Whereas the later case is the procedure used to produce the glass ceramics as discussed in later slides. So the crystallization occurs by nucleation and growth. It may occur on the surface or in the bulk of the glass. The nucleation may be homogeneous nucleation or it can be heterogeneous nucleation. So the processes of nucleation and growth have already been discussed previously, and in the further slides, we will be discussing the phenomena of liquid-liquid phase separation. First, we will discuss liquid-liquid phase separation. If we take some amount of water in a container and add oil to it, then the two form a separate layer and do not mix. That is, the oil and water are immiscible. If the container is closed and shaken vigorously, the oil breaks into droplets which are dispersed in the major phase, that is water. The two, that is oil and water, are still immiscible, but the morphology has changed from a layer structure to drops dispersed in a matrix structure. In glasses also, a single liquid phase can separate into two immiscible phases under certain conditions. This is called liquid-liquid phase separation. A liquidus temperature is called or defined as the temperature at which a crystalline phase begins to separate out from the liquid. The liquid-liquid phase separation can occur above the liquid or below the liquidus. The former is called the stable immiscibility and the later is called subliquidus or metastable immiscibility. Examples of systems in which stable immiscibility occurs are compositions containing divalent metal oxides, example, strontium oxide, calcium oxide, iron oxide, zinc oxide, and magnesium oxide, while the subliquidus immiscibility is found in silicate melts containing Na2O, that is sodium oxide, Li2O, that is lithium oxide, and BaO, that is barium oxide. These systems have an S-shaped liquidus. Now let us discuss about the thermodynamic considerations in liquid phase separations. A single phase would separate into two phases if the process leads to a reduction in the free energy. The free energy of mixing of two phases can be written as delta Gm is equal to delta Hm minus T delta Sm, where G is the Gibbs free energy, H is the enthalpy, and S is the entropy. So students, you can see on the right hand side the figure showing the free energy versus composition at high temperature where the system exists as a single phase. At a sufficiently high temperature, the second term of this equation on the right hand side dominates and the free energy smoothly varies throughout the whole composition range. If the first term is large and positive, or if the temperature is reduced, a maximum and two minima occur in the delta G versus composition plot as the temperature is reduced below a certain temperature called upper critical temperature. This upper critical temperature is also known as absolute temperature, which is shown in the figure. Below this temperature, say T3, so here T3 is absolute temperature or upper critical temperature. So at T3, a common tangent can be drawn to the two minimas. The tangent touches the minima at compositions x1 and x2. Now let's discuss about phase separation by nucleation and growth and by spinodal and decomposition. Let the solution have an average composition. Let G naught be the average free energy of an atom and G be the free energy of any one atom in the solution. The probability of an atom having the free energy, that is G, is given by the Boltzmann distribution, which is given as F of delta G is equal to A times exponential minus delta G by kT, where delta G is equal to G minus G naught. The probability of n atoms having the same energy G simultaneously is F is equal to A times exponential minus n delta G by kT. Assuming the delta G is small and expanding by Taylor series, one gets G is equal to G naught plus 1 by 2 d square G by dx square times x minus x naught square and so on. Neglecting higher order terms as the composition fluctuations, x minus x naught is very small. Now substituting G minus G naught is equal to delta G, we get the probability of a small fluctuation involving n atoms, which is given as F is equal to A times exponential minus n into x minus x naught whole square into d square G by dx square complete divided by 2 kT. From this equation, it is seen that the probability of the fluctuation will be large if the curvature of the free energy curve d square G by dx square is negative. So in this case, the fluctuations will occur simultaneously and spontaneously. Now let us come back to the previous figure in which the composition versus free energy at different temperatures is drawn. The tangent to the two minima touches the minima at points x1 and x2. Points I1 and I2 are the inflection points at which the quantity d2x by dx square, the curvature of the curve, is 0. For compositions between the inflection points, the curvature is negative. However, the curvature is positive outside the composition range between I1 and I2. In the lower diagram, one can see that the locus of the points of the tangency at different temperatures are drawn. This curve has a dome-like appearance and is called binodal curve. Also, drawn is the locus of the points I1 and I2 at different temperatures, shown as a dotted curve within the binodal dome. This curve is called spinodal curve. In the composition range included by the spinodal curve, the curvature is negative. So, any small composition or fluctuation in a solution of this overall composition would be accomplished by a decrease in the free energy, and so it would be stable. The system can easily separate into two compositions differing by a small amount in composition. The system is therefore stable with respect to phase separation. So in this case, any local fluctuation in the composition would grow. The composition of the two phases would change until they attain the composition given by the common tangent, that is x1 and x2. This process of formation of two phases is called spinodal decomposition. The above concept of a decrease in the free energy due to a small composition fluctuation in the spinodal region is further illustrated in this figure. For an initial composition P, small fluctuation leads to compositions Q and R. The free energy change follows the arrow and decreases. The fluctuations can therefore occur and grow. This is the spinodal decomposition. For any composition between the spinodal dome and the binodal dome, the situation is as shown in the figure. In this case, a smaller fluctuation leads to an increase in free energy. This is the situation in nucleation. So in this region, the liquid-liquid phase separation occurs by nucleation and growth. Now let us discuss the spinodal decomposition. The morphology produced in the two cases is quite different, that is, spinodal and binodal. In the case of nucleation and growth, the nuclei of the second liquid form within the parent liquid and grow into spheres. The morphology in this case is called spheres in a matrix microstructure. This can be seen in this figure. So, in the spinodal decomposition, a phase with initially uniform composition separates into two phases which initially differ only slightly in composition, but with time the composition fluctuation sharpens and eventually an initially bicontinuous structure transforms to a droplet structure. However, in case of spinodal decomposition, the morphology is quite different. There are smaller composition fluctuations in the beginning, which we have discussed. The boundaries between two phases are diffused and the two phases are interconnected and spread throughout the whole volume. Both phases will have high degree of connectivity. The interfaces sharpen with time and eventually a morphology similar to that of nucleation and growth is attained. These two morphologies are explained earlier in this figure. Now this table summarizes the differences between the phase separations, nucleation and growth and by spinodal decomposition. So you can see that the parameter, that is phase composition, differs in both the cases. First case is nucleation and growth and second is spinodal decomposition. So at a fixed temperature, the nucleated phase composition remains constant, whereas in case of spinodal decomposition, the composition changes until the equilibrium is achieved. However, if we discuss about interface between phases, these are clearly defined throughout, whereas in case of spinodal decomposition, they are initially diffuse and then become sharpened with time. The third is morphology. In case of nucleation and growth, morphology of spherical particles are of random size with low connectivity. Whereas in case of spinodal decomposition, the non-spherical morphology is observed, which are thread-like and they have high connectivity. So students, let's now summarize what we have learned in this module. So students, we have learned that a liquid phase melts can undergo phase changes in several ways, and these are: it can be using liquid-liquid phase separation by homogeneous nucleation and growth. Second, it can be liquid-liquid phase separation by spinodal composition. Third, crystallization by homogeneous or heterogeneous nucleation. Next is modification into rigid glass and subsequent crystallization to glass ceramic by an appropriate heat treatment. Moreover, we have learned that liquid-liquid phase separation can occur if two minima and a maxima appear in the free energy versus composition plot as the glass melt is cooled. This can happen above the liquid's temperature, in which case it is called stable immiscibility, or below the liquid's temperature. In the later case, it is called metastable immiscibility, and the locus of the minima in the free energy versus composition plot at different temperature leads a dome-shaped curve called binodal curve. So the locus of the inflection points in the free energy versus composition plot produces another curve within the binodal curve, and this curve is called spinodal curve. For compositions between binodal curve and spinodal curve, the phase separation occurs by nucleation and growth. For compositions within the spinodal curve, the free energy reduces even if there is a small fluctuation in composition. So these fluctuations occur simultaneously and grow till there are two phases with compositions corresponding to two free energy minima at that temperature. So in this case of phase separation by nucleation and growth, the morphology consists of droplets of one liquid dispersed in the other liquid. In the case of spinodal decomposition, the two phases are continuously distributed throughout the whole volume. And with the time, the phase boundaries sharpen and eventually droplets in a liquid morphology is attained. Thank you.